100 billion stars. That is what our galaxy holds. For generations, that number made us feel enormous, special, significant, chosen even. James Webb just changed that. In a single image, Webb stared into a patch of darkness no larger than a grain of sand held out at arm's length and discovered thousands of entire galaxies packed inside it, each one carrying hundreds of billions of stars of their own, some carrying trillions. Tonight we travel from the edge of our galaxy to the farthest reaches of light that Webb has ever captured. We will visit galaxies that should not exist by any model we had before. We will stand at the edge of voids so immense they challenge the structure of everything we thought we understood. We will encounter ancient light that left its source before our planet was even a thought in the mathematics of gravity and gas. And at every step, the scale will recalibrate itself in ways that are genuinely difficult to absorb. So we begin where all of this starts, not in a laboratory, not at a chalkboard, not in an observatory dome, but outside on a clear night, somewhere far from the glow of cities, somewhere quiet enough to let your eyes adjust. Look up. If the conditions are right, you will see it. A pale, slightly luminous smear stretching across the sky from one horizon to the other. It has no hard edges. It does not announce itself. It simply lies there, faint and patient, like something half remembered from a dream. That smear of diffuse light is our galaxy, the Milky Way, seen from the inside, edge on, the way you might look at a dinner plate if your eye were resting directly on the surface. Every star you can count individually belongs to it. Every constellation ever named belongs to it. The ancient stories told across every civilization on Earth, the bears and hunters and scorpions and gods drawn in the night sky, all of them are written in the same galaxy. For most of human history, that smear was the universe, the whole of it. The boundary and the interior and the full extent of creation all wrapped into a single band of faint light. People did not know it was a galaxy. The word itself had not been invented in its modern sense. It was simply the sky. The great river of heaven, the road of milk, the spine of night. We now know it is none of those things. We now know that band of light is the combined glow of hundreds of billions of individual suns compressed by distance into something that looks, to the naked eye, like little more than a smudge. And we now know because Webb has shown us beyond any reasonable dispute that what felt like the entire universe is not even a footnote in the true scale of what exists. That shift in understanding did not happen all at once. It came in stages, each one pushing the boundary of the known a little further outward, each one making the previous understanding look smaller by comparison. And the most dramatic of those stages is still unfolding right now, returned to us in data packets from a telescope floating 1 million miles from Earth, collecting light that has been traveling toward us for longer than our planet has existed. But before we can appreciate what Webb is showing us, we have to understand what we are starting from. We have to understand what we actually know about the place we live, the Milky Way, and why even that knowledge was so hard to get. The fundamental problem with studying our own galaxy has always been location. We are inside it. Not near its center, not at a convenient observation point on its outer rim, with a clean view of the whole structure. We are embedded in one of its spiral arms, roughly 2/3 of the way out from the center, surrounded in every direction by the very thing we are trying to understand. Imagine trying to map a city while standing in the middle of its most crowded district. Buildings rise around you in every direction, streets disappear into the distance. You can see what is immediately nearby with some clarity, but the full shape of the city, its edges, its proportions, the way its different neighborhoods relate to one another remains permanently out of sight. That is precisely the situation astronomers have faced for centuries when attempting to understand the Milky Way. You cannot step outside it. You cannot find a vantage point above it. Every observation has to be made from within, using instruments that must see through layers of gas and dust and competing starlight to pick out the signals they are looking for. It is, in some ways, the most fundamentally difficult observational challenge in astronomy. Ground-based telescopes helped, but only so much. They could map the positions of millions of stars, track their motions, study their spectra, infer their distances. But the dust that fills the plane of the galaxy, The dense molecular clouds where new stars are being born blocked visible light from penetrating more than a few thousand light-years in most directions. The galaxy's center itself, where the structure is most dramatic and most informative, was almost completely hidden behind curtains of interstellar dust so thick that optical telescopes could not see through them at all. Radio astronomy changed the game significantly when it came into maturity in the middle of the 20th century. Radio waves travel through dust without difficulty. By mapping the radio emissions of hydrogen gas, the most abundant element in the galaxy, and a reliable radio emitter, astronomers could build a picture of the Milky Way's large-scale structure in ways that optical observations simply could not provide. They identified the spiral arms. They began to trace the central bar, the straight, dense region of stars at the galaxy's core from which the arms extend. They measured the speed at which the galaxy rotates and used that information to calculate its total mass, including the enormous amount of invisible material that gravity demanded must be there even when telescopes could not see it. Infrared telescopes then pushed further still. Infrared light penetrates dust more effectively than visible light. Satellites and ground-based instruments operating in the infrared could peer into regions of the galaxy that had been sealed off from conventional observation. The center of the Milky Way, hidden from optical telescopes by roughly 25,000 light-years of dust and gas, could now be studied in detail. And what was revealed there was extraordinary: a supermassive black hole, designated Sagittarius A*, with a mass equivalent to about 4 million of our suns, sitting at the gravitational heart of everything, surrounded by a dense cluster of stars orbiting at its speeds and distances that, in any other context, would seem physically impossible. By the early years of the 21st century, astronomers had assembled a reasonably confident picture of our galaxy. The Milky Way is a barred spiral galaxy, one of the most common types in the observable universe. It has a central bulge, a flat disk of stars and gas, a halo of older stars and globular clusters extending above and below the plane, and an even larger halo of dark matter invisible to all telescopes but detectable through its gravitational influence extending out to perhaps 10 times the visible radius. The disk itself, where most of the stars and gas reside, spans something in the range of 100,000 light-years from edge to edge. Some newer measurements suggest it may be closer to 120,000 or even 160,000 light-years across when its outermost structures are included. But 100,000 light-years has long been the standard figure used as a reference point. 1 light-year is approximately 6 trillion miles, 6 followed by 12 zeros. A number so large it ceases to have meaning in any ordinary human frame of reference. Multiply that by 100,000 and you have a span of distance that, if you were traveling at the speed of light, the fastest anything can travel in the universe, would take you 100 millennia to cross. Our fastest spacecraft, moving at tens of thousands of miles per hour, would need something on the order of 2 billion years to make that journey. By any sensible comparison to anything on Earth, or anything in human experience, that is an incomprehensible scale. It feels like the kind of number that should settle the question of significance permanently. A galaxy 100,000 light-years across, containing hundreds of billions of stars, each one potentially hosting its own family of planets, how could that not be the whole story? Then James Webb launched, and the whole story turned out to be something else entirely. The James Webb Space Telescope did not launch with the primary goal of making our galaxy feel small. Its mission was directed outward toward the earliest moments of the universe, toward the first light that ever shone after the Big Bang, toward the chemical signatures of distant atmospheres, toward the infrared glow of objects too cold or too far to be visible in ordinary light. Webb was designed to answer questions that had been accumulating for decades. Questions about how galaxies formed in the first place. Questions about the conditions of the early universe. Questions about what lies beyond the reach of every telescope that came before it. But the data Webb returned did something that its engineers and scientists had anticipated in principle, but that still had to be absorbed in full when the images actually arrived. Every comparison it made, every deep field image it returned, every ancient galaxy it detected, every cosmic structure it resolved at distances no previous instrument could reach, reframed the question of our galaxy's scale in terms that were impossible to set aside. Because here's what happens when you stare into a region of deep space with the most powerful infrared telescope ever built. You do not just see distant galaxies, you see how many of them there are. You see how they are distributed, you see how old they are. And you are confronted inescapably with the arithmetic of what you are looking at. The confirmed deep field images that Webb has returned show thousands of galaxies in patches of sky so small that, held to the eye from arm's length, a single grain of sand would cover the entire region. Not a handful of galaxies, not dozens, thousands. Each one a gravitationally bound system of stars, gas, dust, dark matter, and very probably planets. Each one separated from every other by distances measured in millions of light years. Each one containing, on average, somewhere between tens of billions and several trillion individual suns. When you begin multiplying those numbers together, thousands of galaxies per grain of sand-sized patch, multiplied across the billions of such patches that tile the full sphere of the sky in every direction, the total count of galaxies in the observable universe becomes a figure that previous generations of astronomers would have considered an overstatement. Earlier estimates place the galaxy count at around 200 billion. After Webb's deep field observations were incorporated into revised models, some researchers revised that figure upward to approximately 2 trillion. 2 trillion galaxies, each one a complete, independent, ancient, and incomprehensibly vast system of matter. Each one with its own history, its own structure, its own population of stars living and dying on timescales that dwarf the entire span of human civilization. And the Milky Way, our galaxy, the one that contains every human who ever lived and every place we have ever been, is one entry in that list. Not a special entry, not a central entry, just one. That is the context that Webb has given us, and it is only the beginning of what it is teaching us. There is a particular moment in the history of astronomy that serves as the best reference point for understanding what Webb's observations mean, not just scientifically, but in terms of what they do to the way a person perceives their place in the universe. That moment happened in 1995. Astronomers working with the Hubble Space Telescope made a decision that, at the time, struck many of their colleagues as wasteful at best and reckless at worst. They selected a tiny patch of sky near the constellation Ursa Major, the region of the Big Dipper, and pointed Hubble directly at it for 10 consecutive days. This was not a trivial commitment. Hubble time was and remains among the most fiercely competed resources in all of science. Every hour of observation was the result of proposal reviews and committee decisions and months of waiting. Spending 10 days on a single patch of sky that appeared, to every available instrument, to contain nothing at all was the kind of decision that required extraordinary confidence in the underlying logic. The logic was this: if the sky is uniformly filled with galaxies in all directions, then even a patch of sky that looks empty to existing instruments should reveal those galaxies when observed long enough and carefully enough. The strategy was to collect enough photons, enough individual particles of light arriving from whatever might be in that dark patch to build an image of what was actually there. Not a snapshot, but an accumulation. An exposure measured not in seconds or minutes, but in days, gathering light that was arriving in quantities too small to register in any shorter observation. What came back was one of the most consequential images ever produced by human technology. The Hubble Deep Field showed more than 3,000 galaxies in a patch of sky roughly 1/13 the diameter of the full moon. Galaxies of every shape: spirals, ellipticals, irregular tangles of stars that seemed to be in the process of colliding or merging, or simply evolving in ways that had not yet been categorized. Galaxies at a range of distances that corresponded to a range of ages, so that looking across the image was simultaneously looking backward in time, seeing the universe at different points in its history all at once. That image changed everything. It proved conclusively that the universe was not just full of galaxies, but extravagantly, almost recklessly full of them. Every dark patch of sky, no matter how empty it appeared, was in fact densely populated with entire independent universes of stars. They were simply too far, too faint, and too ancient for anything to see them, until Hubble turned its gaze long enough and steady enough to let their light accumulate into an image. The scientific community absorbed the Hubble Deep Field and its implications over the years that followed. Deeper versions of the image were produced. The Hubble Ultra Deep Field, released in 2004, pushed the count higher and the distances further. The Hubble Extreme Deep Field, assembled from thousands of hours of archived Hubble observations, reached even further back in time. Each new image expanded the picture. Each one made the universe larger and more populated than the previous understanding had accommodated. And then, Webb arrived. When the James Webb Space Telescope produced its first deep field image in the summer of 2022, it did not simply extend the Hubble result by a modest increment. It demolished the previous limit entirely. Webb's primary mirror, a segmented gold-coated array 6.5 meters across, built from 18 hexagonal panels and capable of collecting nearly 7 times more light than Hubble's mirror, combined with its suite of infrared instruments to see things that Hubble's detectors could not access. Regardless of how long it observed, infrared light with wavelengths longer than visible red carries information from objects that are too far away, too cold, or too heavily redshifted for visible light telescopes to detect. The expansion of the universe stretches the wavelengths of light as it travels. Light that was emitted as ultraviolet radiation by a galaxy near the beginning of time arrives at Earth. After 13 billion years of cosmic expansion, not as ultraviolet but as infrared. Hubble could not see that light. Webb can, and what Webb sees in that infrared range is extraordinary. The Webb Deep Field images contain galaxies that Hubble could not detect at all. Not because they weren't there. They were always there, but because their light, by the time it arrived at Earth, had been redshifted beyond what Hubble's instruments could register. Some of these galaxies formed within the first few 100 million years after the Big Bang. Their light has been traveling for more than 13 billion years. They represent the universe in its infancy, not just old, but genuinely ancient in a way that requires sitting with for a moment. The universe is approximately 13.8 billion years old. Some of the galaxies detected in Webb's deep field images formed when the universe was less than 400 million years old. That means the universe had not yet lived 3% of its current age when those galaxies began assembling. Stars were already forming. Gravity was already pulling matter into the first great structures. The cosmic web, the large-scale architecture of filaments and voids that organizes everything in the universe into something like a three-dimensional net, was already beginning to take shape. And the Earth did not exist. The Sun did not exist. The molecular cloud from which our solar system would eventually condense was not yet assembled. We were, in the most literal astronomical sense, nowhere. All of that history, all of that ancient light, all of those galaxies that predate our planet by billions of years, is contained in images of patches of sky smaller than a grain of sand held at arm's length. The question that followed from those images was the natural one, the one that anyone looking at them would eventually have to ask. If one tiny patch of sky contains thousands of galaxies, and if every patch of sky has a similar density which observation strongly suggests, then how many galaxies are there in total across the entire observable universe? Estimating that number is not simple. The observable universe is not the same as the universe. It is the portion of the universe from which light has had time to reach us in the 13.8 billion years since the Big Bang. Beyond the observable universe, there may be vastly more, perhaps infinitely more, but we cannot, even in principle, receive information from those regions because their light has not had time to reach us, and, given the accelerating expansion of the universe, never will. Within the observable universe, astronomers have attempted to count galaxies by extrapolating from deep field images. Earlier estimates, based on Hubble data, suggested a total of around 200 billion galaxies. More sophisticated analyses, incorporating data about galaxy sizes and the likelihood that many galaxies are too small or too faint to have been detected even by Hubble, revised that figure upward. After Webb's observations were factored in, some researchers suggested the true total could approach 2 trillion. Others are more conservative. The honest scientific answer is that we have a confident order of magnitude somewhere in the range of hundreds of billions to a couple of trillion, and the exact figure depends on definitions and on how you handle the galaxies that are too small or too ancient to have been directly detected. What is not in dispute is that the number is staggeringly large, that every patch of sky is full of galaxies, and that our galaxy is one of those galaxies not at the center, not distinguished by any particularly exceptional characteristic, simply present as one entry among what may be 2 trillion others. There is a way to try to make that concrete, though it ultimately defeats any ordinary frame of reference. If you were somehow able to look at a different galaxy every second, one per second, without stopping, without sleeping, from the moment the universe formed until now, you would not have finished. At 1 galaxy per second, 2 trillion galaxies would take roughly 63,000 years. That is longer than modern human civilization has existed, and you would still have seen only a fraction. The scale is not a figure you absorb. It is a figure you acknowledge, and then you continue, because there is more to understand. The Milky Way itself, in the context of all this, has a specific position and a specific character worth understanding in some detail. Not because it is exceptional as we have established. It is not, but because understanding what it actually is makes the comparisons to everything else that Webb has found more meaningful. Our galaxy is classified as a barred spiral galaxy. That classification is precise and well supported by decades of observation. The barred part refers to a feature at the center. Instead of spiral arms curving outward directly from a simple central bulge, the Milky Way has an elongated bar of densely packed stars running through its core, and the spiral arms extend from the ends of that bar rather than from the center itself. This bar structure is a real physical feature. Stars within it are measurably distributed differently from stars in the surrounding regions, and its gravitational influence can be detected in the motion of stars throughout the galaxy. The spiral arms themselves are areas of somewhat denser gas and star formation, marked by the concentration of young, bright, blue stars and the glowing gas clouds nebulae where those young stars have recently formed. Our solar system sits in one of these arms, in a region sometimes called the Orion arm or the local arm, roughly 26,000 light-years from the center. That position not quite at the center, not quite at the edge, in one of the arms of a middle-sized barred spiral is about as ordinary as galactic addresses come. If you were assigning cosmic real estate values based on location, our neighborhood would be described as unremarkable. The galaxy rotates, not like a solid disk, not the way a record on a turntable spins, but differentially, with the inner regions completing their orbits more quickly than the outer ones. Our solar system travels around the center of the Milky Way at roughly 515,000 miles per hour. At that speed, which would carry you from New York to Los Angeles in approximately 20 seconds, it takes our solar system about 225 to 250 million years to complete a single orbit around the galactic center. Astronomers sometimes call this period a cosmic year or a galactic year. The Earth is about 18 of those cosmic years old. The last time our solar system was in roughly its current position in its orbit, the dominant land animals on Earth were early dinosaurs. The time before that, the first complex animal life was only just appearing in the oceans. The galaxy's disk, the flat region where the spiral arms and most of the gas and stars reside, is roughly 1,000 light-years thick in the regions we live in, though it thickens toward the center and thins toward the edges. Above and below this disk extends a halo, a more diffuse population of older stars and globular clusters, which are dense spherical groups of ancient stars that were among the first to form in the galaxy's history. Beyond that, extending invisibly but detectably through its gravitational effects, is the dark matter halo, a roughly spherical distribution of material we cannot see, detect directly, or yet fully characterize, but which accounts for the majority of the Milky Way's total mass. The total mass of the Milky Way, including all visible matter and the dark matter halo, is estimated at somewhere between 700 billion and 2 trillion times the mass of our Sun, with most estimates clustering around 1 to 1.5 trillion solar masses. That sounds enormous. In the context of the full range of galaxy masses in the observable universe, our galaxy is medium-sized, larger than most of the dwarf galaxies that populate the universe in enormous numbers, but smaller than the most massive elliptical galaxies, which can contain tens of trillions of solar masses of material. Our nearest large galactic neighbor, the Andromeda Galaxy, officially designated M31, is somewhat larger than the Milky Way and sits at a distance of approximately 2.5 million light-years. It is, by a considerable margin, the most distant object visible to the naked eye from Earth under dark sky conditions, appearing as a faint smudge slightly larger than the full moon. Andromeda and the Milky Way are gravitationally bound. They are moving toward each other at roughly 70 miles per second and are expected to collide and eventually merge in approximately 4 to 5 billion years, producing in the end a single large, elliptical galaxy that some astronomers have informally named Milky Way. Together with several dozen smaller satellite galaxies, including the Large and Small Magellanic Clouds, which are visible from Earth's southern hemisphere as detached patches of the Milky Way and Andromeda form the core of what is called the local group. The local group spans roughly 10 million light-years and contains somewhere around 50 to 80 galaxies, depending on how the boundaries are drawn and how many faint dwarf galaxies are included in the count. The local group itself is part of a larger structure, the Virgo supercluster, a collection of galaxy groups and clusters spanning roughly 110 million light-years and containing perhaps 100 galaxy groups. And the Virgo supercluster is now understood to be one lobe of an even larger structure called Laniakea, a supercluster of superclusters spanning roughly 500 million light-years and containing the mass of hundreds of quadrillions of suns, organized into a complex network of filaments flowing gravitationally toward a region of concentrated mass called the Great Attractor. Each of these structures exists within the cosmic web, the large-scale architecture of the universe itself, in which galaxy clusters and filaments form a foam-like three-dimensional pattern, with immense voids of near emptiness separating the dense regions. The cosmic web emerged from tiny fluctuations in the density of matter in the very early universe and grew into its current form over billions of years through the accumulation of gravitational influence. At every level of this hierarchy, galaxy, group, cluster, supercluster, cosmic web, our position is modest. We are in a mid-sized galaxy at the edge of a small group at the outskirts of a supercluster in a filament of the cosmic web. Nothing about that address marks us as central or exceptional. It is simply where we are. And now Webb is showing us that this address, this whole elaborate hierarchy from our planet, through our galaxy, through our supercluster, is itself embedded in a universe so populated with similar addresses that the imagination buckles trying to contain it. The word deep, in the phrase deep field, deserves a moment of attention because it is doing something more than simply describing direction. When astronomers look deep into the sky, past the nearby stars, past the edge of our galaxy, past the nearby galaxies and galaxy clusters, they are not only looking far in space, they are looking back in time. This is one of the most philosophically striking facts in all of science, and it follows from something simple. Light travels at a finite speed. The speed of light, approximately 186,000 miles per second, or about 670 million miles per hour, is the fastest any information can travel through the universe. That speed is extraordinary by any earthly standard. Light can circle the Earth more than 7 times in a single second. It travels from the Moon to Earth in about 1.3 seconds, from the Sun to Earth in about 8 minutes. But the universe is vast enough that even at the speed of light, the travel time for photons becomes cosmologically significant. Light from the Andromeda Galaxy, our nearest large neighbor, takes 2.5 million years to reach us. When you look at Andromeda in the night sky, you are seeing it as it was 2.5 million years ago. The galaxy you see tonight is an image from the early Stone Age of human prehistory, when our ancestors were among the first hominids using stone tools. Light from the most distant galaxies Webb can detect has been traveling for more than 13 billion years. Those galaxies are so far away, and the universe has expanded so much during the time their light has been in transit, that they now sit in terms of co-moving distance, accounting for expansion somewhere around 30 to 46 billion light-years away. When we look at them in Webb's images, we are seeing them not as they are today, but as they were when the universe was less than 1 billion years old. They may look completely different now, more evolved, more structured, possibly merged with other galaxies into something bearing no resemblance to what Webb is showing us. We cannot know, because the light showing us their current state will not arrive here for billions of years, if ever. This means that every deep field image is a time machine. It is a cross-section through cosmic history nearby galaxies as they looked millions of years ago, intermediate distance galaxies as they appeared billions of years ago, and the most distant objects as they existed in the first few 100 million years after the Big Bang. Looking at such an image carefully is like reading the geological record of the universe, with each layer of distance corresponding to a layer of time. Webb has extended that geological record further back than any previous instrument. Its infrared sensitivity allows it to detect the light of objects that existed when the universe was less than 5% of its current age. Some of the galaxies it has detected formed within the first 300 to 400 million years after the Big Bang, a period so early in cosmic history that the universe was still in many ways structurally simple. The dark matter halos that would anchor future galaxies only beginning to coalesce. The first generation of stars only beginning to live and die and seed the universe with the heavier elements that would eventually make planets and chemistry and life possible. Those first stars designated population 3 stars in the stellar classification scheme, though none have yet been directly confirmed with certainty by direct observation, are thought to have been enormous, burning hot and fast, living for only a few million years before exploding as supernovae and scattering their contents through the surrounding gas. Their deaths enriched the early universe with carbon, oxygen, nitrogen, and other elements that the Big Bang itself did not produce in significant quantities. They were the first step in a chain of stellar generations, each one living, dying, and contributing the products of its nuclear furnace to the next that eventually produced, billions of years later, the molecular cloud that became our solar system. The iron in our blood, the calcium in our bones, the oxygen in every breath. All of it was forged in stellar interiors and scattered by stellar deaths across billions of years of cosmic history before finding its way, through an improbable chain of events, into the particular arrangement of atoms that constitutes a living human being on a small rocky planet orbiting an ordinary star in one arm of a mid-sized barred spiral galaxy. Webb is looking at the beginning of that chain. It is seeing the universe before most of that chain had even started. And in doing so, it is providing the deepest context yet for understanding what the Milky Way is, where it came from, and just how young and modest it is in the full sweep of cosmic time. There is a particular category of finding that has emerged from Webb's observations that deserves its own extended consideration, not because it is the most visually spectacular aspect of what the telescope has returned, but because it is, in many ways, the most scientifically consequential. It is the discovery of galaxies that, according to the models astronomers had built and refined over decades, should not exist in the form Webb is finding them. These are sometimes called the impossible galaxies in popular descriptions, though that phrasing is slightly misleading. They are not impossible in any fundamental physical sense. They clearly exist, because Webb has detected them. What makes them challenging is the timeline. These galaxies are too massive, too structured, and too chemically evolved to have formed in the amount of time available to them given their measured distances and the corresponding ages that those distances imply. They are, by the standards of the best models available before Webb launched, premature. Galaxies that should have required more time to build than the universe had allowed. To understand why this matters, it helps to understand what those models actually predict and where they came from. The standard model of cosmology, sometimes called lambda CDM, for reasons that relate to its mathematical structure, incorporating a cosmological constant in cold dark matter, is not a casual guess or a rough sketch. It is one of the most precisely tested frameworks in the history of science, built from decades of observations of the cosmic microwave background, the large-scale structure of the universe, the behavior of distant supernovae, the distribution of galaxy clusters, and dozens of other independent lines of evidence. It describes a universe that began approximately 13.8 billion years ago in an extremely hot, dense state, expanded and cooled, formed the first atoms after roughly 380,000 years, and then gradually built structure through the gravitational amplification of tiny density fluctuations that were present from the beginning. In this model, the sequence of structure formation follows a particular logic. Dark matter, which interacts gravitationally, but not electromagnetically, meaning it cannot emit, absorb, or scatter light collapsed first into clumps and halos, providing the gravitational scaffolding into which ordinary matter subsequently fell. Small structures formed before large ones in this scenario. The first objects to coalesce were relatively small dwarf galaxy-sized clumps that then merged, over time, into progressively larger structures. Large galaxies like the Milky Way assembled gradually through a combination of gas accretion and the merging of smaller predecessors, a process that played out over billions of years. This picture, known as hierarchical structure formation, made specific predictions about what the early universe should look like. At very high redshifts, corresponding to very early times, the model predicted that galaxies should be small, irregular, relatively low in mass, and only beginning the process of building the stellar populations that more evolved galaxies like ours contain. Massive, well-organized galaxies with large populations of old stars should not be present in the early universe because they had not yet had time to form. The universe at that epoch was simply too young for the gravitational and stellar evolutionary processes that produce massive galaxies to have run to completion. Webb is finding objects that challenge this prediction in ways that are not easily dismissed. Some of the galaxies detected at extreme distances corresponding to times when the universe was only a few 100 million years old appear to have stellar masses and stellar populations that, by the standards of hierarchical formation models, should not be present. They are too big. They have too many stars. Some of them show spectral signatures suggesting that their stellar populations include stars that themselves have had time to live, evolve, and die, which implies that star formation in those galaxies began even earlier than the galaxy's already early observed epoch, pushing the timeline of the first stars further back toward the Big Bang than the models had comfortably accommodated. One class of findings that generated particular attention involves what are sometimes called red and dead galaxies at high redshift massive galaxies that appear to have already stopped forming new stars by the time we observe them in Webb's data, even though they exist at an epoch when the universe was less than 1 billion years old. A galaxy that has stopped forming stars is one that has exhausted or expelled most of its star-forming gas, a process that takes time and typically involves energetic feedback from supernovae and from the active galactic nucleus. At the galaxy's center, which is powered by its central supermassive black hole, for a galaxy to have gone through all of that formed, built a large stellar population, and then quenched its own star formation in less than 1 billion years requires a pace of activity that was not anticipated by standard models. Some of the early Webb findings were reported with considerable excitement in the popular press and even in some scientific publications, with language suggesting that the standard model was in crisis. That characterization was, and remains, premature. Science does not work on the timescale of news cycles. The standard model is not overturned by a handful of anomalous objects detected in a new telescope's early observing runs. What those objects do is create a productive tension, a set of observations that push on the edges of the existing framework and demand either explanation within that framework, or, if no adequate explanation can be found, revision of the framework in a targeted and evidence-supported way. The scientific community's response to the Webb early galaxy findings has been appropriately measured. Some researchers have proposed explanations that preserve the core of the standard model while adjusting specific assumptions. For instance, that the efficiency of star formation in the early universe may have been higher than the models assumed, meaning that the available gas was converted into stars more rapidly, allowing early galaxies to build more mass in less time. Others have explored whether the mass estimates for some of these galaxies may be inflated by assumptions that do not fully account for the particular properties of early stellar populations. Still, others have suggested that some of the objects being identified as high redshift galaxies may turn out, upon further observation, to be at different distances or to have properties that can be reconciled with existing models in ways not immediately apparent from the initial data. These are all legitimate scientific responses. They represent the standard process by which new data is incorporated into existing understanding, not by declaring revolution, but by careful examination, alternative hypothesis testing, and incremental revision. Science advances through exactly this kind of productive friction between observation and theory. At the same time, it would be a misrepresentation to suggest that the tension Webb has revealed is trivial or easily resolved. Several of the anomalous objects have survived initial scrutiny and remain genuinely difficult to accommodate within existing frameworks without modification. The cumulative effect of Webb's early observations in this area is not merely a small correction to previous estimates, but something that may, as the data accumulate and the analysis matures, require substantive revision of assumptions about early star formation, early galaxy assembly, or the behavior of dark matter halos in the early universe. Whatever the eventual resolution, the galaxies Webb has found in the early universe are real. Their light is ancient. Their existence at the distances and epochs where Webb has detected them is confirmed. And their presence requires explanation either within the existing model or, if that model proves insufficient, through a revised one that accounts for what Webb is seeing. That process of confrontation between data and theory is how scientific understanding grows, and Webb has accelerated that process dramatically. There is another category of finding from Webb's observations that connects to the question of our galaxy's scale in a different way, not through the discovery of ancient galaxies in the early universe, but through the mapping of our own galaxy's relationship to the larger structures around it. The Milky Way does not exist in isolation. No galaxy does. Galaxies are social objects. They exist in groups and clusters, interact gravitationally with their neighbors, exchange material, occasionally collide, and are continuously shaped by the larger environment in which they sit. Understanding our galaxy's scale and character requires understanding not just what it is in itself, but what it is embedded in. The structure of the universe on the largest scales, the cosmic web of filaments, nodes, and voids, was not discovered by Webb. Its broad outlines were established by earlier surveys and observations, most notably by large-scale galaxy redshift surveys that mapped the three-dimensional distribution of hundreds of thousands and eventually millions of galaxies across significant fractions of the observable universe. What emerged from those surveys was a picture of the cosmos that was, by any aesthetic standard, unexpectedly beautiful and structurally complex. The universe is not uniformly distributed with galaxies. It is organized into a web-like pattern that emerged from the same density fluctuations that seeded the formation of the first stars and galaxies. In this web, matter is concentrated along filaments, elongated structures that can stretch hundreds of millions of light-years, with galaxy clusters sitting at the nodes where filaments intersect. Between the filaments and nodes are voids, regions of space that are almost entirely empty of galaxies, spanning hundreds of millions of light-years across, occupying the vast majority of the universe's volume while containing only a tiny fraction of its matter. The scale of the voids is one of the most startling features of the cosmic web. A single large void might span 300 million light-years across. Inside that void, there are few galaxies. Some, in the densest voids, have no detected galaxies at all across their entire interior. The void's interior is not truly empty. It contains sparse gas and possibly dark matter in low concentrations. But the contrast between the packed filaments and the nearly empty voids is dramatic. The universe appears as a kind of foam or sponge when viewed at the largest scales, with the matter concentrated in the thin walls and threads of the structure and the vast majority of space occupied by emptiness. Our galaxy and the local group sit in a relatively modest part of this web. We are not in a particularly dense region, not at the intersection of major filaments, not inside a rich cluster with thousands of member galaxies. We are in a sparse group, in the outer reaches of a supercluster, in a region of the cosmic web that is, by cosmological standards, quiet. This location has consequences. The Milky Way's history of galaxy mergers has been relatively calm compared to galaxies in dense cluster environments, where gravitational interactions and collisions are frequent. Our relative isolation has allowed the Milky Way to develop without the dramatic disruptions that frequently reshape galaxies in busier cosmic neighborhoods. Webb is contributing to the mapping of these large-scale structures in several ways. Its ability to detect and precisely measure the redshifts of large numbers of galaxies using spectroscopic instruments that decompose galaxy light into its component wavelengths and measure the characteristic shift toward the red. That indicates recession velocity and therefore distances, improving the three-dimensional maps of the universe at redshifts that previous surveys could not reach in comparable detail. Webb is extending the map backward in time, showing how the cosmic web structure appeared in earlier epochs and allowing astronomers to trace how it evolved from the barely perceptible density fluctuations of the early universe into the dramatic filaments and voids of the present day. The picture that emerges from these observations reinforces every point about the Milky Way's scale and position. Our galaxy is a small feature in a sparse group at the edge of a modest supercluster, itself one of many thousands of superclusters distributed along the filaments of the cosmic web. The web itself, in its full extent, spans the entire observable universe, roughly 93 billion light-years in diameter, and our position within it is no more distinguished than a single grain of sand on a beach that stretches to the horizon in every direction. Among the most intriguing and persistent puzzles that Webb's observations have sharpened is one that existed before Webb launched, but has become significantly more pressing in the years since the question of the universe's expansion rate and whether the two primary methods of measuring it are telling a consistent story. The expansion of the universe is one of the foundational facts of modern cosmology. The universe is not static. It is growing. Every region of space is being stretched by the same process that has been operating since the Big Bang, carrying galaxies apart from one another at rates that increase with distance. This was discovered in the late 1920s by Edwin Hubble and his collaborators, who showed that the recession velocities of galaxies, the speed at which they appeared to be moving away from us, were proportional to their distances. More distant galaxies recede faster. This relationship, now called the Hubble law, implies an expanding universe, and tracing that expansion backward implies a moment of origin, the Big Bang. The rate of that expansion is described by a number called the Hubble constant, typically denoted h0 and measured in units of kilometers per second per megaparsec, meaning, for every megaparsec of distance, a megaparsec is about 3.26 million light-years. Galaxies are receding at a speed given by h0 kilometers per second. Measuring this constant precisely is one of the central goals of observational cosmology, because its value constrains the age, size, and ultimate fate of the universe. There are two main methods for measuring the Hubble constant. One uses the cosmic microwave background, the faint glow of radiation left over from when the universe first became transparent, about 380,000 years after the Big Bang, to infer the expansion rate from the physics of the early universe. The most precise measurements of the cosmic microwave background, particularly from the Planck satellite, give a Hubble constant of approximately 67 to 68 kilometers per second per megaparsec. The other method uses a cosmic distance ladder, a series of overlapping measurement techniques calibrated against each other, starting with nearby distances measured by stellar parallax, extending to the use of pulsating stars called Cepheid variables, and reaching out to the use of type Ia supernovae as standard candles at cosmological distances. This method consistently gives a Hubble constant of approximately 73 kilometers per second per megaparsec. The difference between 67 and 73 might seem small in absolute terms, but it is enormously significant in the context of precision cosmology. Each measurement is reported with uncertainties that put these two values in substantial tension. They do not overlap within their respective error bars. This means that either one or both measurements contain systematic errors that have not yet been identified, or the universe is actually behaving differently than the standard model assumes, and the discrepancy is real. This discrepancy is known as the Hubble tension, and it has been one of the most actively discussed problems in cosmology for several years. Before Webb launched, there was some hope that the tension might be resolved by improving the precision of the distance ladder measurements, specifically by getting better measurements of the Cepheid variable stars that form a crucial rung in the precision ladder. Cepheids are stars that pulsate with a period related to their intrinsic brightness, making them useful distance indicators. But measuring Cepheids in distant galaxies with Hubble was difficult because the telescope could not always cleanly separate individual Cepheid stars from the crowded stellar backgrounds of their host galaxies. Webb, with its superior infrared sensitivity and resolution, has improved those Cepheid measurements substantially. The result, however, has not been to reduce the Hubble tension. Webb's Cepheid measurements have confirmed the distance ladder result rather than pushing it toward agreement with the cosmic microwave background value. The tension persists, and, if anything, the improved precision of Webb's measurements has made it harder to attribute the discrepancy to measurement error alone. The implications of this are genuinely uncertain and genuinely significant. If the Hubble tension is real, if it reflects an actual inconsistency in the standard cosmological model rather than an unidentified systematic error, then something in our understanding of the universe needs revision. Proposed explanations range from the existence of exotic forms of early dark energy that affected the universe's expansion in its first few 100,000 years, to modifications of the standard model's treatment of dark matter, to more radical proposals involving new physics. None of these proposals has yet achieved consensus. The Hubble tension connects to the story of our galaxy's scale in a fundamental way. The expansion of the universe determines the relationship between redshift and distance, and therefore the ages and distances of the ancient galaxies Webb is detecting. If the Hubble constant is actually 73 rather than 67, the universe is slightly younger than the Planck value suggests, about 12.5 billion years old rather than 13.8 billion. That shrinks the available time for the most ancient galaxies Webb has detected to have formed, making the impossible galaxies problem potentially more acute. If the universe is older rather than younger, the problem eases somewhat. The two tensions, the early massive galaxy problem and the Hubble tension, are not necessarily connected, but they are both pulling on the same framework. And the combination of the two has reinvigorated discussions about whether the standard model requires modification at a more fundamental level than simple parameter adjustment. What Webb is doing in both cases is providing the high-precision observational anchor that these discussions require. Before Webb, many of the measurements involved had uncertainties large enough to leave significant room for alternative interpretations. Webb's data is precise enough to close off some of those escape routes and force the confrontation between theory and observation to become more direct. One aspect of our galaxy's structure that is worth dwelling on in the context of Webb's observations is the nature of the central region, not just the supermassive black hole at its core, which has received considerable attention, but the broader environment of the galactic center and what it reveals about our galaxy's history. The center of the Milky Way is a region of extraordinary density and activity. Stars in the galactic center are packed together at densities millions of times higher than in the solar neighborhood. The supermassive black hole, Sagittarius A*, sits at the gravitational heart of this dense central region, surrounded by a cluster of stars, some of them moving so fast in their orbits that they complete a full circuit around the black hole in just a few years. These stars, observed continuously for decades by teams of astronomers using large ground-based telescopes equipped with adaptive optic systems that correct for the blurring effect of Earth's atmosphere, provided the primary evidence that confirmed the presence of a supermassive black hole at the galactic center before its direct image was obtained. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A times a blurry but unmistakable ring of glowing gas, marking the shadow of the black hole against the bright emission of infalling material. The image showed a structure roughly consistent with predictions, but the detailed properties of the gas and the environment around the black hole continue to be studied and refined. Supermassive black holes at the centers of galaxies are not passive passengers. They are active participants in the evolution of their host galaxies, particularly when they are in phases of active accretion feeding on gas that falls toward them, releasing enormous amounts of energy in the process. This energy, in the form of radiation and powerful jets of particles moving close to the speed of light, can heat and expel the surrounding gas, shutting off star formation across large regions of the galaxy. This mechanism, called AGN feedback, for active galactic nucleus feedback, is thought to be responsible for the quenching of star formation in massive galaxies and is incorporated into the best models of galaxy evolution. The Milky Way's central black hole is currently relatively quiet. It is not actively feeding at a high rate. The galaxy is not producing the brilliant quasar emission that would be visible across the universe if Sagittarius A times were accreting as rapidly as the supermassive black holes in more active galaxies. There is evidence that it was more active in the past. X-ray and gamma-ray observations have detected what appear to be enormous bubble-like structures, called Fermi bubbles, extending above and below the galactic plane for tens of thousands of light years, likely produced by a period of more intense activity millions of years ago. What this history tells us is that the Milky Way has a past that its current quiet appearance does not fully advertise. Like many galaxies, it has gone through periods of more intense activity, and the consequences of those periods are written into its structure in the distribution of its stellar populations, in the chemical enrichment of its gas, in the large-scale outflows that previous bursts of activity have driven outward from the center. Webb is contributing to the understanding of this class of phenomena across cosmic history by observing galaxies at a wide range of distances and therefore epochs, building a picture of how AGN activity evolved over time. The very early universe, Webb's observations suggest, was a time of intense black hole growth and AGN activity. Many early galaxies contained active nuclei, pouring energy into their surroundings at rates far exceeding anything seen in the present-day Milky Way. That activity shaped the early galaxy population in profound ways and is one of the mechanisms proposed to explain why some early galaxies appear to have quenched their star formation so rapidly. The contrast between the active early universe and the relatively quiet present-day Milky Way is itself a reflection of the galaxy's age and evolutionary state. The Milky Way formed most of its stars billions of years ago. It is not in a particularly active phase of construction. It is, by cosmic standards, a mature galaxy in a relatively settled middle age, still forming some new stars, still evolving, but no longer in the furious growth phases that characterized its early history and that Webb is now observing in younger galaxies at cosmological distances. There is a region of the sky that has, for much of the history of astronomy, been a source of frustration and fascination in roughly equal measure. It is called the zone of avoidance. The zone of avoidance is not a region of space where galaxies are absent. It is a region of the sky centered on the plane of the Milky Way where the dust and gas in our own galaxy's disk is so dense that it blocks the light of the galaxies beyond it from reaching us in wavelengths that optical telescopes can detect. It is called the zone of avoidance because it is, for optical astronomers, a zone they are forced to avoid not by choice but by physics. The practical consequence of the zone of avoidance is that our map of the large-scale structure of the universe has a gap running through it, centered on the galactic plane. That corresponds to roughly 20% of the sky. Inside that gap, we cannot see what optical surveys have mapped everywhere else. We know there must be galaxies there. The same density of galaxies that fills the rest of the sky should, in principle, continue into the zone. But we cannot directly observe them in the wavelengths that most galaxy surveys use. The Great Attractor, the massive concentration of matter toward which our galaxy, the local group, the Virgo supercluster, and indeed, much of the surrounding cosmic neighborhood is gravitationally flowing, sits, with perfect inconvenience, largely within the zone of avoidance. Its existence was deduced not from direct observation, but from the peculiar velocities of galaxies in our neighborhood. The fact that galaxies were moving in a consistent direction that could not be explained by the visible mass alone, implying a large hidden concentration of mass behind the galactic plane. Observations in radio wavelengths, and particularly in infrared wavelengths which penetrate dust more effectively than visible light, have partially pierced the zone of avoidance and allowed astronomers to begin mapping what lies behind it. Several rich galaxy clusters have been discovered in the zone, and the picture of the Great Attractor as a complex of clusters and filaments centered on a massive supercluster called the Norma cluster has become clearer. Webb's infrared capabilities are relevant here as well. While Webb is primarily focused on cosmological observations at extreme distances, its sensitivity in infrared wavelengths extends the ability to probe obscured regions of the sky and detect galaxies that are hidden from optical surveys. The full mapping of the zone of avoidance, and therefore the full characterization of the large-scale structure in our immediate cosmic neighborhood, is a gradual process to which multiple instruments contribute. And Webb is part of that ongoing effort. What the zone of avoidance represents, in the broader context of this story, is a reminder that even our ability to understand our own galactic neighborhood is constrained by the structure of the galaxy we live in. The very feature that makes the Milky Way spectacular when seen from inside the dense plane of gas and stars that produces that pale smear across the night sky is the same feature that blocks our view of the universe in the most interesting direction. We are, in a very literal sense, partially blinded by our own home. The dark matter that fills the halo of our galaxy, and the halos of every galaxy Webb can detect, is one of the most significant and persistent mysteries in modern physics and cosmology. It is worth spending some time with it here, because it is central to the story of galactic structure at every scale, and because Webb's observations bear on some of the questions surrounding it in ways that are only beginning to be understood. Dark matter is real. That much is not in serious scientific dispute. The evidence for its existence comes from many independent lines of observation that converge on the same conclusion. There is more gravitational influence in galaxies and galaxy clusters than can be accounted for by the visible matter alone. Stars in the outer regions of galaxies orbit at speeds that, according to straightforward application of the laws of gravity, should only be possible if there is substantially more mass present than the stars and gas that can be detected. Galaxy clusters bend the light of more distant galaxies behind them, an effect called gravitational lensing, to a degree that requires more mass than is visible. The large-scale structure of the cosmic web, the distribution of filaments and voids, would not have the pattern it has unless dark matter were present in the quantities that models require. What dark matter actually is, what kind of particle or particles it consists of, remains unknown. Decades of experiments searching for dark matter particles through their weak interactions with ordinary matter have not produced a confirmed detection. Various candidates have been proposed and searched for, from a class of hypothetical particles called WIMPs, weakly interacting massive particles, to axions, to sterile neutrinos, to more exotic possibilities involving entirely new sectors of physics. None of them has been confirmed. This is genuinely puzzling. Dark matter accounts for roughly 27% of the total energy content of the universe, more than 5 times the contribution of ordinary visible matter, which constitutes only about 5% of the total. The rest, approximately 68%, is the even more mysterious dark energy, the name given to whatever is responsible for the accelerating expansion of the universe. Between dark matter and dark energy, the known physics of the standard model of particle physics accounts for only 5% of what the universe is made of. The remainder, the overwhelming majority of everything, remains uncharacterized at the particle level. Webb cannot directly detect dark matter. No telescope can by definition. Dark matter does not interact with light. But Webb can probe the distribution of dark matter indirectly, through gravitational lensing the bending of light from distant sources by the gravitational influence of dark matter concentrations in the foreground. Webb's sensitivity and resolution make it exceptionally good at detecting and characterizing gravitational lensing effects. Both the dramatic arcs and rings produced by the strongest lensing, and the subtle statistical distortions produced by weaker lensing distributed across large areas of sky. These lensing measurements allow astronomers to map the distribution of dark matter in galaxy clusters and in large-scale structure in ways that were not possible with previous instruments. Webb is contributing to a steadily improving picture of how dark matter is distributed across the universe, how it is concentrated in halos around galaxies, how those halos are shaped, how the dark matter distribution connects to the visible structure of the cosmic web. For our galaxy specifically, the dark matter halo extends far beyond the visible disk, perhaps to radii of several 100,000 light-years, making the true size of the Milky Way, if you include its dark matter halo, substantially larger than the 100,000 light-year disk figure that is commonly quoted. The same is true of essentially every galaxy. The visible parts are nested within dark matter halos that are typically several times larger. The universe's structure, at every scale, is shaped primarily by dark matter. The visible matter that telescopes detect is, in a real sense, just the luminous decoration on a scaffolding of invisible mass. The implications of this for the story of our galaxy's scale are straightforward but worth making explicit. When we say the Milky Way is 100,000 light-years across, we are describing the visible disk. When we include the dark matter halo, the galaxy's gravitational influence extends much further. When we zoom out to the level of galaxy clusters and superclusters, the dominant structural material is dark matter. The visible galaxies are embedded in dark matter concentrations that were assembled before the galaxies themselves, and that determined where the galaxies would form. We live, in other words, inside a structure built primarily from material we cannot detect and do not yet understand. The Milky Way is small relative to the cosmos, but it is also, in a sense, larger than it looks, wrapped in an invisible halo of matter that dwarfs its visible component and connects it gravitationally to the broader cosmic web. One of the most consequential discoveries in the history of cosmology came not from a galaxy survey or a deep field observation, but from the study of exploding stars at cosmological distances. In 1998, two independent teams of astronomers studying Type Ia supernovae stellar explosions used as standard candles to measure cosmic distances announced a finding that contradicted the most natural expectation for the universe's future. The universe was expected to be decelerating. Everything in the universe has gravitational mass, and gravity pulls things together. The expansion of the universe should therefore be slowing down over time the mutual gravitational attraction of all the matter in the universe working against the expansion, the way that throwing a ball upward is opposed by Earth's gravity. The question before 1998 was not whether the expansion was decelerating, but how fast, whether it was decelerating slowly enough that the universe would expand forever, or fast enough that expansion would eventually reverse and the universe would recollapse. What the supernova observation showed instead was that the expansion was not decelerating at all. It was accelerating. The universe was expanding faster now than it was in the past, and the rate of acceleration was increasing. This meant that something was working against gravity on the largest scales, something with a repulsive gravitational effect, something that filled space uniformly and dominated the dynamics of the universe's expansion. This something was named dark energy, and it has been the subject of intense theoretical and observational effort ever since. Dark energy's nature remains unknown. The simplest description of it, a cosmological constant, a term that Einstein originally included in his field equations, and later famously called his greatest blunder before the accelerating expansion was discovered, and the term was vindicated, treats dark energy as a property of space itself, a fixed energy density that does not dilute as the universe expands, and therefore comes to dominate the universe's energy budget over time as matter and radiation thin out. Current data are consistent with this interpretation, but they do not rule out alternative forms of dark energy that vary over time, or that have more complex behavior. The consequences of dark energy's dominance are profound and direct. The accelerating expansion means that distant galaxies are receding from us faster and faster. Galaxies beyond a certain distance, the Hubble horizon, are receding faster than light, which means their light will never reach us. Over cosmic timescales, this horizon moves closer. Galaxies that are currently detectable will eventually recede beyond the point at which their light can ever reach us. The observable universe is, in a deep sense, shrinking not in physical size, but in the fraction of what exists that we can ever observe. For our galaxy, this means that the current era, when billions of galaxies are visible across the sky, when the cosmic microwave background is still detectable, when the full richness of the cosmic web can in principle be mapped, is actually a privileged moment in cosmic history. Billions of years from now, the accelerating expansion will have carried most of the observable galaxies beyond our horizon. A civilization arising in the far future would look out at a nearly empty sky and have far less information available about the universe's structure and history than we do today. We exist, in other words, at a cosmologically fortunate time, not in any mystical sense, but in the simple sense that the universe is currently in a state where its history is still partly readable in the distribution of light across the sky. Webb is making the most of that window, collecting as much information as the current epoch allows before the accelerating expansion continues its work of separating the universe's structures from one another. The discovery of dark energy also reframes the future of our galaxy and its neighbors in a specific way. While the accelerating expansion will eventually carry most of the universe's galaxies beyond our reach, it does not affect gravitationally bound structures on smaller scales. The local group, our galaxy, Andromeda, and their satellite galaxies, is gravitationally bound tightly enough that the accelerating expansion will not pull it apart. Instead, the local group will eventually merge into a single giant elliptical galaxy. The clusters and superclusters in our cosmic neighborhood, bound by the gravity of their concentrated mass, will similarly persist as islands in an accelerating sea. the very long-term fate of the universe dominated by dark energy, with structures slowly evaporating as their constituent stars burn out and their compact remnants cool, is a subject of active research and speculation, with the details depending on the true nature of dark energy and on physics that is not yet fully understood. But the broad outlines are clear enough to say that the Milky Way, in any meaningful sense of its future, will eventually cease to be the structure it is today. Its stars will die, its gas will be exhausted, its remnants will disperse or be absorbed. The timescales involved are so vast, hundreds of trillions of years, in some scenarios much longer, that they strain any human attempt at comprehension. But that future, however distant, is part of the full picture of what our galaxy is. It is not eternal. It is not permanent. It is a temporary structure assembled from material that formed in the Big Bang, shaped by processes that ran for billions of years, and ultimately destined to dissolve back into something else on timescales that dwarf its entire current history. There are other galaxies in the observable universe that dwarf the Milky Way so completely that the comparison requires its own careful unpacking. Not because knowing about them changes anything practical, but because they provide the clearest possible illustration of just how variable galactic scale can be and how modestly our own galaxy fits into the full distribution. IC 1101 is one of the largest known galaxies in the observable universe. It sits at the center of a rich galaxy cluster approximately 1 billion light-years away. It is an elliptical galaxy, a type that, in general, contains older stellar populations and less active star formation than spiral galaxies like the Milky Way, having already consumed or expelled most of its star-forming gas through its history of mergers and AGN feedback. IC 1101 spans approximately 6 million light-years in its longest dimension. The Milky Way, at 100,000 light-years across, could fit inside IC 1101 60 times over. It is estimated to contain roughly 100 trillion stars, perhaps 500 times the stellar population of our galaxy. If our galaxy is a single page in a book, IC 1101 is the entire library. This is not a unique object. There are other galaxies of comparable or even larger scale, though IC 1101 is among the most extreme confirmed examples. The largest galaxy clusters contain tens of thousands of individual member galaxies, each one a gravitationally bound system of stars. The brightest cluster galaxies, massive ellipticals that sit at the centers of the richest clusters, have grown to their enormous sizes through billions of years of mergers, with smaller galaxies that fell into the cluster and were absorbed. At the opposite end of the scale, the universe is populated by enormous numbers of dwarf galaxies, small, irregularly structured collections of stars with masses and stellar populations a tiny fraction of the Milky Way's. The Milky Way itself has dozens of satellite dwarf galaxies in orbit around it, slowly being tidally disrupted and absorbed. The Large and Small Magellanic Clouds, the most prominent of these satellites, are themselves not negligible structures. The Large Magellanic Cloud is a few tens of thousands of light-years across and contains tens of billions of stars, but they are dramatically smaller than the Milky Way and are in the process of eventually being incorporated into it. The full distribution of galactic masses across the observable universe spans roughly 5 orders of magnitude from the smallest dwarf spheroidal galaxies, which contain only a few million stars, to the most massive giant ellipticals, which contain tens to hundreds of trillions. The Milky Way sits comfortably in the middle of this distribution, perhaps slightly above the median, neither a dwarf nor a giant. Just a reasonably large and reasonably well-organized spiral in a reasonably quiet neighborhood. That ordinariness is, in its own way, remarkable. For most of human history, our galaxy was the cosmos. Then it became the largest thing we knew. Then it became one galaxy among a few observable neighbors. Then it became one galaxy among hundreds of billions. And through all of that scaling, it remained ordinary, unremarkable at each new level of comparison, fitting comfortably into whatever distribution the universe turned out to contain. There is something almost philosophically elegant about that consistency. The Milky Way is not an outlier. It does not sit at the extreme of any distribution. It is a representative member of the galactic population average in mass, average in size, average in structure, average in position, and yet it is the place from which all of astronomy has been conducted. Everything we know about the universe beyond our galaxy has been learned from within this perfectly ordinary one. Webb's observations extend across a wide range of scientific programs that go beyond galaxy counts and early universe structure. Some of those programs bear directly on questions about our own galaxy and its context in ways that deserve attention. One of the most celebrated early results from Webb involved the detailed chemical analysis of exoplanet atmospheres, planets orbiting stars in our own galaxy. Using a technique called transmission spectroscopy, Webb observed the light of distant stars as their planets passed in front of them, measuring the tiny fraction of starlight that filtered through the planetary atmospheres. Different molecules absorb light at different wavelengths, leaving characteristic fingerprints in the spectrum that can identify what the atmosphere contains. Webb's sensitivity in the infrared made it possible to detect molecular signatures in exoplanet atmospheres with a precision that no previous telescope could match. Early results confirmed the presence of water vapor, carbon dioxide, and other molecules in planetary atmospheres at distances of hundreds of light years. More speculative detections of molecules that, on Earth, are associated with biological processes have been reported. Though none of these have yet reached the threshold of confirmed scientific consensus, and all are subject to ongoing analysis and alternative explanation. These observations are relevant to the story of our galaxy's scale in an indirect but meaningful way. The exoplanets Webb is studying are, in cosmic terms, nearby within our own galactic arm, separated from us by distances of tens to hundreds of light years rather than millions or billions. They are our immediate galactic neighborhood, the local texture of the Milky Way on a scale that, while incomprehensibly large by human standards, is intimate compared to the distances involved in galaxy surveys and deep field observations. The fact that planets exist in large numbers around stars throughout our galaxy, a conclusion supported by decades of exoplanet observations, suggesting that most stars have planetary systems, means that the Milky Way's 200 to 400 billion stars are accompanied by at least that. Many planets, and probably several times more. The question of whether any of those planets harbor life, a question that Webb is beginning to address, at least at the level of atmospheric chemistry, is one of the most profound that science has ever entertained. Webb cannot answer that question definitively, and it may never be able to. Detecting biosignatures in planetary atmospheres is an extraordinarily difficult observational challenge, even with the world's most powerful infrared telescope. But it is beginning to build the vocabulary and the methodology that future observatories plan successors to Webb with even larger collecting areas and more sensitive instruments will use to investigate the question more thoroughly. What that broader context adds to the story of our galaxy's scale is a layer of possibility. The Milky Way is small relative to the cosmos. It contains hundreds of billions of stars. Those stars are accompanied by hundreds of billions of planets. Some of those planets are rocky, orbit in the temperature range where liquid water can exist on their surfaces, and have atmospheres that Webb is beginning to be able to characterize. Somewhere in that enormous population of worlds, the conditions for chemistry, for biology, and potentially for something we would recognize as life may exist or may already have existed, or may arise in the future. That is not a certainty. It is a possibility suggested by the scale of the sample and the apparent prevalence of the necessary conditions. But the possibility alone, the mere fact that the Milky Way is large enough and old enough and chemically rich enough to have produced at least one world with life on it, is itself a remarkable statement about what our ordinary, medium-sized, quietly positioned galaxy contains. Step back, as far back as the mind will allow, further than the local group, further than the Virgo supercluster, further than the filaments of Laniakea, further even than the boundaries of the observable universe as we currently define them. Imagine the full three-dimensional structure of everything that Webb has helped map, helped refine, helped extend backward in time toward its earliest beginnings. Imagine the cosmic web in its entirety, a structure of breathtaking complexity, spanning 93 billion light-years in every direction from where we stand. Organized into a pattern that no human eye could ever take in whole, but that the mathematics of cosmology and the data of generations of telescopes have assembled, piece by piece, into something we can now describe with genuine confidence. The map would show filaments, immense threads of galaxy clusters stretching across hundreds of millions of light-years, glowing faintly with the combined light of billions of stars concentrated along their lengths. It would show nodes where those filaments intersect, places where gravity has concentrated matter into the richest clusters, the densest assemblies of galaxies in the observable universe, places where thousands of galaxies inhabit volumes of space only a few tens of millions of light-years across. And it would show voids, the vast, nearly empty regions that occupy the overwhelming majority of the universe's volume. Places where the density of matter is so low that hundreds of millions of light-years can pass with almost no galaxy to interrupt the darkness. The cosmic web is not static. It is not the same today as it was 1 billion years ago, or 5 billion years ago, or 10 billion years ago. Webb's ability to observe the universe at multiple epochs, to look at nearby galaxies as they are today, and at distant galaxies as they were billions of years in the past, has provided an increasingly detailed picture of how this web assembled itself over cosmic time. How the first density fluctuations, seeded in the earliest moments after the Big Bang, grew through gravitational amplification into the filaments and nodes of the present day. How dark matter halos formed first, then pulled ordinary matter in after them, then lit up as the gas inside them collapsed into the first stars and galaxies. How those early galaxies merged and grew and fed their central black holes, and shaped their own environments through the energy those black holes released, until what began as a nearly featureless sea of hydrogen and helium became the richly structured cosmos we can now observe in Webb's images. Zoom in by a factor of thousands from the full cosmic web, and a single supercluster appears. Laniakea 500 million light-years across, containing hundreds of galaxy groups and clusters organized into a complex network of smaller filaments flowing gravitationally toward the dense mass concentration at its core, the region called the Great Attractor. Laniakea is not a gravitationally bound structure in the same sense that a galaxy cluster is bound. The accelerating expansion of the universe will eventually pull its outer regions apart, and it will not persist as a coherent unit over cosmic timescales. But today, in the current epoch, it represents the largest structure to which our galaxy can be said to belong in any meaningful gravitational sense. Zoom in further from Laniakea. The Virgo supercluster resolves into view a smaller structure, roughly 110 million light-years across, of which our galaxy's neighborhood forms one modest appendage. The Virgo cluster itself, a rich cluster of more than 1,000 galaxies centered on the massive elliptical galaxy M87. The galaxy whose supermassive black hole produced the first direct black hole image in 2019 sits at the gravitational center of the Virgo supercluster. Our local group sits at the outskirts, well removed from the cluster center, subject to the Virgo cluster's gravitational influence, but not yet falling into it on any human-relevant timescale. Zoom in once more. The local group materializes as a sparse collection of a few dozen galaxies scattered across roughly 10 million light-years. At its center, two dominant galaxies, Andromeda and the Milky Way, hold the group together with their combined gravity. Surrounding them, a retinue of smaller companions, the Triangulum galaxy, a modest spiral that is the third largest member of the group, the Large and Small Magellanic Clouds orbiting the Milky Way, a collection of dwarf spheroidals and dwarf irregulars scattered through the group's volume, most of them attached gravitationally to one of the two dominant galaxies. And at the center of one of those two dominant galaxies, not the larger one, not Andromeda, but the slightly smaller barred spiral on the other side of the group, one modest star among hundreds of billions, orbiting at a distance of 26,000 light-years from the galactic center in one of the spiral arms, is the Sunday. And around the Sun, at a distance of 1 astronomical unit, 1/8 minutes of light, is the Earth. This is the map, verified, measured, observed, refined over decades of increasingly capable astronomy and sharpened by Webb into its most precise form yet. Every layer of it is supported by evidence. None of it is speculation. And at every layer of it, our position is modest, not at a center, not at a boundary, not at a node of particular density or significance, simply embedded in the structure at a perfectly ordinary location. That is where we are. That is the confirmed answer to the question of our place in the universe. And the question that follows the one that the map itself does not answer is what it means to be here. There is a concept in the history of astronomy and philosophy that has been revisited repeatedly as each new expansion of the known universe has required a corresponding revision of where humanity sits within it. The concept has various names, but its core is simple: the recognition that we are not at the center, not at the top, not at the most important location in whatever structure we find ourselves embedded in. The Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is not the center of the universe. There is no center of the universe. Each of those recognitions, when it first arrived, was experienced by many people as a kind of loss. The Copernican recognition that the Earth moves around the Sun rather than the other way around was resisted for decades, not only because it contradicted established authority, but because it displaced humanity from the privileged position that a central location seemed to confer. The subsequent discoveries that our Sun is one star among hundreds of billions in a galaxy, that our galaxy is one among what may be 2 trillion, that the universe has no center from which any location can claim priority, each extended and deepened that displacement. But there is another way to think about what each of these discoveries actually did. Rather than diminishing us, each one expanded the known. Each one added to the inventory of what exists, what has happened, what the universe contains. The Copernican revolution did not make the universe less interesting. It made it more interesting by revealing a solar system with a dynamics and a structure that a geocentric model could not explain. The discovery that the Milky Way was one galaxy among billions did not make the Milky Way less remarkable. It made the cosmos more remarkable by revealing the full population of which our galaxy is a member. Webb is the latest chapter in that long sequence of expansions. It has not taken anything away. It has added ancient galaxies, impossible structures, precise measurements of expansion, refined maps of the cosmic web, the first steps toward atmospheric characterization of other worlds. Every image it has returned has made the universe larger, more populated, more ancient, and more structured than the previous understanding accommodated. The Milky Way, in this expanded picture, is genuinely small. That is not a metaphor, and it is not a rhetorical device. It is a measurement. Our galaxy is 100,000 light-years across. Some individual galaxies are 6 million light-years across. Our local group contains roughly 50 to 80 galaxies. Some clusters contain thousands. Our supercluster spans 500 million light-years. The observable universe spans 93 billion light-years. At every level of the hierarchy, we are a minor entry. But minor in size is not the same as minor in significance. Those are two different measurements, and only one of them can be made with a telescope. The question of what Webb has revealed about how small our galaxy really is cannot be fully answered without addressing the most fundamental comparison of all. Not just the comparison between the Milky Way and other galaxies, but the comparison between the Milky Way and the full temporal scope of the universe it exists within. Our galaxy is not only small in space, it is young in time. The universe is approximately 13.8 billion years old. The Milky Way formed after the first generation of stars had already lived and died, seeding the universe with the heavier elements that its own stars would require. Current estimates place the formation of the Milky Way's oldest stellar populations at roughly 13 to 13.5 billion years ago, meaning our galaxy is genuinely ancient in human terms, but was not among the very first. Structures to form in the universe. The galaxy's web is detecting at extreme distances forming within the first few 100 million years after the Big Bang predate our galaxy by hundreds of millions to over 1 billion years. The oldest stars in the Milky Way's halo, the ancient globular clusters that orbit the galaxy like scattered relics of its earliest phases, formed in conditions that existed before the Milky Way itself had taken its current shape. They are fossils of a different cosmic epoch, assembled when the universe was still raw and young, and the grand architecture of the cosmic web was only beginning to consolidate from the primordial density fluctuations. Those ancient stars, now visible to telescopes as dense spherical clusters of dim red and orange suns, are the nearest thing our galaxy has to a living memory of the universe's infancy. But those ancient stars are exceptions in our galaxy's population. The bulk of the Milky Way's stars, including our own Sun, formed long after the galaxy's initial assembly. The Sun is approximately 4.6 billion years old, meaning it formed when the universe was already 2/3 of its current age. Our solar system is not ancient by galactic standards. It is a latecomer, assembled from gas that had already been through multiple stellar generations, enriched by the supernova deaths of earlier stars into the complex chemical mixture that made rocky planets, carbon chemistry, and eventually biology possible. This temporal context matters for understanding the Milky Way's place in the universe. We are not just small in space, we are late in time. The universe was building galaxies and stars and complex structures for more than 9 billion years before the Sun formed. The heavy elements in every living thing on Earth, every carbon atom, every iron atom, every oxygen atom passed through the interiors of stars that lived and died before our solar system existed, in a galaxy that was already billions of years old when our star was born. Webb makes this temporal dimension vivid in a way that no previous telescope could. When it detects a galaxy at a redshift corresponding to a look-back time of 13.4 billion years, it is showing us a structure that existed before the Milky Way had formed in any recognizable sense. When it resolves the spectral signatures of that galaxy and identifies the elements present in its stars and gas, it is reading a chapter of cosmic chemical history that predates everything in our solar system by an interval that makes all of human history look instantaneous. The universe has been building and evolving and producing galaxies for most of its life without any contribution from us or our galaxy or our star. The Milky Way appeared roughly 2/3 of the way through cosmic time so far, formed in conditions shaped by everything that came before it, and has since been evolving in a universe that was already ancient and structured and chemically complex by the time our galaxy's disk took its current spiral form. This is not a reason for despair. It is simply the correct account of where we fit in the timeline as latecomers to a universe that was already full of history before we arrived. Inheritors of a chemical and structural legacy built by processes and objects that will never be directly observed, only inferred from the evidence they left behind. One of the most instructive exercises for putting the Milky Way's scale in proper perspective is not to compare it to the largest or most impressive things Webb has found, but to trace the full chain of scales from the largest structures in the observable universe down to the most familiar human dimensions, to walk the ladder from top to bottom and feel each rung beneath your feet. Begin at the top. The observable universe spans approximately 93 billion light-years in diameter. That is the full extent of the region from which light has had time to reach us. Within it, the dominant structural pattern is the cosmic web filaments of galaxy clusters and superclusters separated by immense voids. Step down. A typical large supercluster structures like Laniakea, Perseus Pisces, the Shapley supercluster spans a few 100 million to perhaps 1 billion light-years. Inside a supercluster, galaxy clusters are distributed along filaments, each cluster containing hundreds to thousands of individual galaxies. Step down again. A large galaxy cluster, the Coma cluster, the Perseus cluster, the Virgo cluster, spans tens of millions of light-years. Within it, the member galaxies move through the intracluster medium, occasionally colliding and merging, their stars and gas slowly being incorporated into the most massive members. Step down once more. The local group, our home cluster, spans roughly 10 million light-years small by cluster standards, sparsely populated, quiet. Our two dominant galaxies, Andromeda at 2.5 million light-years, the Milky Way at our feet. Step down. The Milky Way itself 100,000 light-years across. The distance from our position to the galactic center, 26,000 light-years. The distance from our position to the edge of the visible disk, about 50,000 light-years in the direction away from the center. Step down. The distance from the Sun to its nearest stellar neighbor, Proxima Centauri, approximately 4.2 light-years. 4 light-years is about 25 trillion miles. The Sun and Proxima Centauri are typical neighbors in the Milky Way's disk, not unusually close, not unusually far. Most stars in our galactic neighborhood are separated from their nearest neighbors by a few light-years. Step down. The solar system itself, from the Sun to the outermost reaches of the Oort cloud, the diffuse shell of comets that surrounds the solar system at distances of up to a light year or more spans perhaps 2 light years. The planets are contained within a much smaller volume. The orbit of Neptune, the outermost recognized planet, has a radius of about 30 astronomical units, 30 times the Earth-Sun distance, or roughly 2.8 billion miles. Step down. The Earth 8,000 miles across. A mote of rock and water and atmosphere, orbiting an ordinary star at a comfortable distance, small enough to be photographed whole from the outer solar system as a pale blue dot in the dark. That is the full chain, from 93 billion light-years down to 8,000 miles, each step a reduction by roughly a factor of 1,000, give or take. Each step revealing a smaller structure, nested within the larger one above it. And at the bottom of the chain, the planet where the instruments were built that allow us to measure the chain in the first place. Webb lives at one of those steps specifically. It orbits around the second Lagrange point, about 1 million miles from Earth, well within the solar system, barely off the bottom rung of the ladder. From there, it looks up outward, backward in time, and illuminates the rungs above with a clarity no previous instrument could provide. There is a particular quality to the light that Webb collects that deserves to be appreciated for what it actually is, beyond the scientific content it carries. Every photon in a Webb deep field image began its journey as an emission event, an electron dropping to a lower energy state in a star or a gas cloud, releasing a quantum of energy as light. That event happened in a galaxy that may have existed before the Milky Way was born, in a star that may have lived and died billions of years before the Sun formed, in conditions that no human observer will ever be close enough to witness directly. The photon then traveled through intergalactic space, not empty space, but the diffuse medium between galaxies, which contains thin gas and the microwave background radiation and the gravitational influence of dark matter for a time measured in billions of years. During that journey, the universe expanded. The space through which the photon was traveling grew larger, and the photon's wavelength grew with it, stretching from whatever it was at emission, perhaps ultraviolet light from a hot young star, perhaps visible blue light, to the infrared wavelengths at which Webb's detectors operate. The photon arrived at Webb's primary mirror, one of the 18 hexagonal gold-coated beryllium segments that together form a surface 6.5 meters across, having traveled further, and for longer, than any human voyage ever taken or imagined. Webb's mirror reflected that photon toward its secondary mirror, which directed it through one of the telescope's instrument packages, where it was detected by an array of sensors cooled to temperatures near absolute zero, converted into an electrical signal, encoded as digital data, and transmitted back to Earth, where it was decoded, processed, combined with millions of other photons collected over hours of observation, and assembled into an image that human eyes can look at on a screen. That chain of events, from the emission of a photon in a galaxy 13 billion years ago to its detection in an instrument built by human hands, is, when considered in full, one of the most remarkable chains of causation in the history of the universe. It connects the universe's infancy to a product of one of its most recent evolutionary developments. It represents the universe, in a very real sense, finding a way to observe itself. This is not a metaphor invented for rhetorical effect. It is a physical description of what Webb's observations actually are. The light was always going to travel. It did not know it was heading toward a mirror. The mirror did not exist for most of the photon's journey. The species that built the mirror did not exist for most of the photon's journey. And yet, through the particular sequence of events that produced a planet with the right conditions, and on that planet, a form of life with the cognitive capacity to understand the universe and the technological capacity to build instruments to observe it, the photon's arrival was caught, recorded, and turned into knowledge. The universe is not doing this intentionally. There is no evidence of purpose in any of this at the cosmological level, but that does not diminish it. The accidental nature of the connection that the history of the universe happened to produce among its 2 trillion galaxies. One ordinary spiral in one quiet group that developed the capacity to look at all the others is, if anything, more remarkable than any purposeful arrangement would be. It was not designed. It happened. Among the things Webb has confirmed about the large-scale structure of the universe is something that carries a particular kind of philosophical weight, not because it is surprising from a physics standpoint, but because of what it implies about our relationship to what we observe. The observable universe is finite. Not because the universe itself is finite. Whether the universe beyond the observable portion is finite or infinite is a question that physics cannot yet answer with certainty, but because of the finite speed of light and the finite age of the universe. We can only see the portion of the universe from which light has had time to reach us in the 13.8 billion years since the Big Bang. Everything beyond that horizon is, in principle and in practice, inaccessible. Not just difficult to observe permanently beyond the reach of any observation, because no information from those regions can ever reach us. And the accelerating expansion of the universe is, very slowly, reducing the size of our observable horizon. As expansion carries distant galaxies away faster and faster, the photons they emit are increasingly stretched and diluted. Eventually, galaxies that are currently visible will recede beyond the point where their light can ever reach us, and they will vanish from the observable universe not because they cease to exist, but because the expanding space between us and them became too vast for light to cross. This means that the universe we can observe is not a permanent endowment. It is a function of the current moment in cosmic history. Earlier observers in a younger universe, before the accelerating expansion had had as much time to operate, had a different observable universe. Later observers in an older universe, after more galaxies have receded beyond the horizon, will have a smaller one. We exist in a particular window of cosmic time, and within that window, the observable universe contains a particular inventory of structures and histories. Webb is reading as much of that inventory as its instruments allow. There is something worth sitting with in that observation. The light from ancient galaxies that Webb is collecting now, the photons that left their sources 13 billion years ago, will never be available to collect again. Once they pass our detectors, they are gone. The opportunity to observe the early universe is not indefinitely available. The signals are faint, the distances are vast, and the expansion of the universe is continuously working to dilute and redshift the information those photons carry. Webb's observations are, in a sense, a record made at the last possible moment before the universe's own dynamics erase the opportunity. That urgency, implicit but real, gives Webb's scientific program a character that goes beyond normal research timelines. The questions it is addressing are not questions that can simply wait for a later, better instrument. Some of the observations Webb is making will be difficult or impossible to improve upon, not because of engineering limitations, but because the universe itself is moving on and taking the evidence with it. Understanding what Webb has revealed about the Milky Way's scale requires, at some point, a direct engagement with the numbers themselves. Not to overwhelm, but to anchor. Numbers are the language in which cosmic scale is actually expressed, and without at least attempting to hold some of them in mind, the comparisons remain abstract in a way that prevents them from landing with their full weight. The Milky Way contains an estimated 200 to 400 billion stars. The range reflects genuine uncertainty. Counting stars in our own galaxy is complicated by the same dust that obscures large regions from optical observation, and different measurement methods and assumptions produce different estimates. For simplicity, 300 billion is often used as a representative figure. 300 billion. To get some sense of that number, if you could count one star per second, counting 300 billion stars would take nearly 9,500 years. The counting would have started before the first cities were built. It would not be finished now, and you would have counted just one galaxy, our own. The observable universe contains an estimated 1 to 2 trillion galaxies. If each of those galaxies contains an average of 100 billion stars, a conservative estimate. Since many galaxies contain far more, the total number of stars in the observable universe is somewhere in the range of 106 sextillion. That is a 1 followed by 23 zeros. The number of grains of sand on all the beaches and deserts of Earth is estimated at around 7 quintillion, a 1 followed by 18 zeros. There are roughly 10,000 times more stars in the observable universe than grains of sand on Earth. Each of those stars, on average, is thought to host at least one planet. Many host multiple. The total number of planets in the observable universe is therefore comparable to, or larger than, the total number of stars somewhere in the range of numbers that cease to mean anything to human intuition and simply have to be acknowledged. Against that backdrop, the Milky Way's 300 billion stars constitute 0.000000003% of the total stellar population of the observable universe. Our solar system's contribution to the mass of the Milky Way is roughly 1 part in 300 billion. The Earth's mass is about 1 part in 333,000 of the Sun's. A human body contains roughly 7 octillion atoms, 7 followed by 27 zeros, each one assembled from elements manufactured in stellar nuclear furnaces over billions of years. At every level of this hierarchy, the numbers point in the same direction. The universe is vast. The structures within it that we think of as large solar systems, stars, galaxies, are, at the scale of the full cosmos, extraordinarily small. And the objects we navigate daily cities, buildings, bodies are, even relative to those small structures, so tiny as to be effectively invisible. But here is the critical thing that the numbers alone do not convey. The same hierarchy of scale that makes a human body cosmically minuscule also makes it extraordinarily complex. A star is simple by comparison. It is a ball of plasma governed by a small set of nuclear and gravitational processes, cycling through a predictable evolutionary sequence over millions or billions of years. A human body contains trillions of cells, each containing meters of DNA encoding billions of base pairs, each participating in networks of biochemical interaction of staggering intricacy. The universe that produced galaxies and stars also produced, in at least one location we know of, this level of complexity, and did so in a galaxy that is, by every spatial and temporal measure, perfectly ordinary. Size and complexity are not the same thing. Mass and organization are not the same thing. The Milky Way is small relative to the observable universe, but it is the only location we know of where the products of stellar nucleosynthesis, the carbon, oxygen, nitrogen, phosphorus, and other elements manufactured in stellar interiors over billions of years were assembled by the processes of chemistry and biology operating on planetary surfaces over geological timescales into structures capable of reflecting on their own origin and their own place in the cosmos. Whether that has happened elsewhere in other galaxies, around other stars, on other planets in our own galaxy is a question Webb is beginning to address, and that future telescopes will pursue with growing capability. But the answer, whatever it turns out to be, does not change the fundamental strangeness of the fact that it happened here at all. The concept of a cosmic address, the nested hierarchy of structures within which we locate ourselves, is useful for organizing the information that Webb and its predecessors have provided. But it has a limitation worth acknowledging. A cosmic address describes location. It does not describe history. And the history is at least as important as the location for understanding what we are and where we came from. The atoms in your body have a history that begins in the Big Bang. In the first few minutes after the Big Bang, the universe was hot and dense enough for nuclear fusion to occur, converting some of the primordial protons into helium nuclei and small quantities of lithium. The universe cooled quickly, and this period of Big Bang nucleosynthesis ended after a few minutes, leaving a universe that was about 75% hydrogen and 25% helium by mass, with trace amounts of heavier elements. That was the raw material. Nothing in that inventory could support the kind of chemistry that underlies biology. No carbon, no oxygen, no nitrogen, no phosphorus, no sulfur, no iron. The periodic table was nearly empty, and the universe was almost entirely made of the 2 simplest elements. The first stars changed that. Massive, short-lived, burning through their fuel in millions rather than billions of years. The first generation of stars used nuclear fusion in their cores to build heavier elements from hydrogen and helium-carbon, oxygen, neon, magnesium, silicon, and eventually, in the final stages of the most massive stars, iron and nickel. When those stars exhausted their fuel and could no longer sustain fusion against the inward pressure of their own gravity, they collapsed and exploded as supernovae, releasing in a matter of seconds the energy of billions of years of stellar burning. and scattering their enriched contents through the surrounding gas. That process, stellar nucleosynthesis, followed by supernova dispersal, has been operating throughout the history of the universe, building the inventory of heavy elements in the interstellar medium of galaxies generation by generation. Each generation of stars forms from gas that is slightly more chemically enriched than the gas from which the previous generation formed. The Sun, a third generation or later star, formed from a molecular cloud that had been enriched by the deaths of many stellar predecessors. Its planets, including Earth, formed from the same enriched material. The carbon in every organic molecule in your body was fused in stellar cores. The oxygen in every breath was expelled from dying stars. The iron in your blood was forged in supernova explosions that preceded the formation of the solar system by billions of years. You are, in the most literal chemical sense, made of star stuff, not poetically, not metaphorically, but as a factual description of the provenance of the atoms you are composed of. Webb is observing the early stages of this process, the first stellar populations, the earliest supernovae, the first chemical enrichment of the universe at redshifts that correspond to times when the universe was young and the stellar generations were just beginning to cycle. The spectral signatures it detects in early galaxies carry information about the chemical composition of those ancient stellar populations, allowing astronomers to trace the history of element production across cosmic time and build a quantitative picture of how the universe went from the nearly empty chemical palette of the Big Bang to the rich periodic table that makes planets and chemistry and life possible. That history, the history of the atoms themselves, is part of what makes the Milky Way's smallness a more complicated statement than the numbers alone suggest. Yes, our galaxy is small relative to the cosmos, but it is the result of 13 billion years of stellar processing of nuclear reactions in stellar interiors, of supernovae, of the gradual enrichment of the interstellar medium, of the condensation of enriched gas clouds into new generations of stars and planets. Its smallness in space does not diminish the depth of its history in time. It is a mature, chemically evolved, structurally organized product of 13 billion years of cosmic development, and that development is written into every atom it contains. Webb has also been revealing, with increasing clarity, the nature of the relationship between supermassive black holes and the galaxies they inhabit, a relationship that turns out to be far more intimate and far more consequential than earlier models had fully appreciated. Every large galaxy appears to contain a supermassive black hole at its center. The masses of these black holes range from a few million to several tens of billions of solar masses, and they are tightly correlated with the properties of their host galaxies, particularly with the mass of the galaxy's central stellar bulge. This correlation, the fact that larger bulges tend to host larger black holes, suggests a deep connection between the growth of the black hole and the growth of the galaxy. A coevolution played out over billions of years through processes that are still being characterized. When a supermassive black hole is actively accreting, drawing in large amounts of gas from its surroundings, it becomes what astronomers call an active galactic nucleus, or AGN. In the most extreme cases, AGN can produce luminosities that outshine their entire host galaxy by factors of hundreds or thousands, powered by the conversion of gravitational potential energy into radiation as infalling material spirals into the black hole. These extreme AGN are called quasars, and they were far more common in the early universe than they are today. Webb has been detecting quasars and AGN at extreme redshifts in the first few 100 million years after the Big Bang, and finding that some of them are powered by black holes of surprisingly large mass for such an early epoch. A black hole containing 1 billion solar masses or more, present when the universe was less than 1 billion years old, raises immediate questions about how such an object could have grown to that size in the available time. Black holes grow by accretion, and there are physical limits to how quickly they can accrete, known as the Eddington limit, that make it difficult to explain the rapid growth required to produce billion solar mass black holes in the early universe by straightforward accretion alone. Various mechanisms have been proposed to resolve this puzzle, seeding the black holes with unusually massive initial seeds from the collapse of very massive early stars, or from direct collapse of large gas clouds under the right conditions in the early universe. or from the merger of many smaller black holes? None of these mechanisms has been confirmed, and the question of how the first supermassive black holes grew so quickly remains an active area of research. What Webb's observations of early AGN and quasars are revealing is that the co-evolution of black holes and galaxies, the intimate relationship between these central dark objects, and the stellar systems that surround them, was already underway in the universe's first billion years. The feedback processes by which AGN influence their host galaxies, regulating star formation by heating and expelling gas, were operating in the early universe just as they operate in the galaxies Webb can observe at lower redshifts. The architecture of modern galaxies, including our own Milky Way, was being shaped by these processes from the very beginning. For our galaxy, the legacy of this co-evolution is present but relatively quiet. Sagittarius A*, our central black hole, is currently in a low accretion state. The Milky Way is not producing a quasar. But the evidence of past AGN activity, the Fermi bubbles, the distribution of stellar populations in the galactic bulge, the enrichment of the gas in the inner galaxy, all testify to a past in which our galaxy's central black hole played a more energetically active role. The Milky Way's current quiet state is not its permanent condition. It is one phase in a longer history of activity and quiescence. The particular emotional quality that Webb's images produce in many people who spend time with them is worth examining directly rather than simply invoking. It is a quality that has been described in various ways: awe, vertigo, wonder, humility, but none of these quite captures what it actually is. It is something more specific than any of those words, and it has to do with scale and time operating simultaneously rather than separately. When you look at a Webb deep field image, that photograph of thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length, you are simultaneously confronting spatial scale and temporal depth. The galaxies in the foreground of the image, the bright ones with clear spiral or elliptical structure, are tens to hundreds of millions of light years away. They are not particularly ancient by cosmic standards. They appear as they did in the relatively recent cosmic past. The smaller, redder, less resolved objects in the background are further billions of light years, billions of years in the past. The faintest, smallest, reddest specks, at the limit of detection, are at the edge of what any current instrument can see 13 billion light years away, 13 billion years in the past, existing when the universe was in its infancy. All of those objects, the nearby spirals, and the ancient smudges, and everything in between are present in the same image, the same frame, covering the same tiny patch of sky. Distance and time are mapped together in a single photograph. Looking at it carefully, you are not just seeing far, you are seeing when. The image is a cross-section of cosmic history, the universe's autobiography, laid open to a depth of 13 billion years in a frame you could cover with a fingernail. There is no word in ordinary language for what that image actually is. Experientially, it is more than a photograph. It is a record of time. It is evidence of depth, not just spatial depth, but historical depth, the accumulated depth of 13 billion years of cosmic development, all of it producing structures that were shining long before anything on Earth existed, and whose light has only now arrived at a mirror built by one of those Earth-born structures. The encounter with that image, if you give it the time it deserves, does something to ordinary perception that is hard to describe, and that does not go away. The sense of scale that it instills is not abstract. It becomes, with enough exposure, a background condition, a steady awareness that the sky above is not a ceiling but a depth, that every direction you look is also a direction through time, that the darkness between the stars is not emptiness, but a medium through which ancient light is continuously arriving. That awareness is what Webb has made more precise, more populated, more ancient, and more vivid than any previous instrument. It has not invented the depth was always there. It has simply revealed it more completely. The significance of the James Webb Space Telescope in the history of human inquiry cannot be fully assessed while it is still operating, still returning data, still producing findings that require years of analysis and peer review and follow-up observation before their full implications are understood. The significance of a tool is best measured by what it ultimately produces, and Webb's full production is years from complete. But some things can already be said with confidence. Webb has confirmed and sharpened the picture of our galaxy's smallness in a cosmos of extraordinary scale. It has detected galaxies in the early universe that challenge and are pushing against the edges of the best models of cosmic structure formation. It has improved measurements of the universe's expansion rate in ways that deepen rather than resolve the existing tension in cosmological models. It has begun the work of characterizing the atmospheres of planets in our own galaxy, starting the long process of searching for chemical signatures of biology beyond Earth. It has extended the map of the universe backward in time further than any previous instrument, revealing the earliest epochs of galaxy formation with a clarity and detail that no previous technology could provide. Each of those contributions is significant on its own. Together, they represent a step change in our understanding of the cosmos, not a revolution that overturns everything that came before, but an expansion that adds depth and precision and new questions to a picture that was already extraordinary. The story of how small our galaxy really is the story Webb is telling through its images, and its data is not a story about diminishment, it is a story about scale. About the actual, measured, confirmed dimensions of the structure we inhabit. About what it means to exist in a universe of 2 trillion galaxies, on a planet orbiting an ordinary star in one arm of a mid-sized barred spiral, at the outskirts of a sparse local group, in the outer reaches of a modest supercluster, in one filament of a cosmic web that stretches to the limits of what light can ever carry to us. That story has no moral in the conventional sense. The universe does not offer one. The scale does not care about our response to it. The ancient galaxies did not form in order to humble us. They formed because gravity and gas and time did what gravity and gas and time do in the conditions that existed in the early universe before any consciousness existed anywhere to observe them. But we are here now, observing. And the observation itself, the fact that we built Webb, that we designed it and tested it and launched it and unfolded it and calibrated it and pointed it at the dark and collected the light that came back, is not a trivial thing. It is not something that the scale of the universe diminishes. If anything, the scale of the universe makes it stranger and more remarkable that the observation is happening at all. The Milky Way is small. The numbers confirm it at every level of comparison. Our galaxy is one entry among 2 trillion. Our solar system is one system among hundreds of billions. Our planet is one world among a number too large to hold in mind. Our civilization has existed for an eye blink of cosmic time. And we built a telescope with a mirror the size of a dining table and placed it 1,000,000 miles from Earth in the cold dark of space and pointed it at a patch of sky smaller than a grain of sand and caught the light of galaxies that existed before our planet was born. That is the full picture. Not just the smallness, but the reach. Not just the scale, but what we did with the knowledge of the scale. Not just the 2 trillion galaxies, but the fact that one of them, this ordinary, mid-sized, quietly positioned barred spiral contains the only known place in the observable universe that looked at the rest of it and asked what it means. The answer is still being assembled. Webb is still collecting light. The data is still being analyzed. The models are still being tested and revised. The questions Webb has opened are as important as the questions it has answered. And in many cases, they are more important because the questions we do not yet know how to ask are always the precursors to the most significant discoveries. What we do know is this. Begin with one image, a single photograph taken by James Webb Space Telescope, a patch of sky so small you could cover it with a grain of sand held at arm's length. Inside that image, thousands of galaxies, each one containing hundreds of billions of stars, each one a complete, independent, ancient island of light built over billions of years of gravity and gas and time. Look at that image long enough and something happens to the numbers. They stop being numbers. They become something closer to a felt sense, not quite fear, not quite awe, but something that sits between the two and does not have a name in any language. Because the experience it describes did not exist until we had the instruments to produce it. This is what Webb has given us. Not just revised galaxy counts or improved measurements of cosmic expansion or refined maps of large-scale structure. a new felt sense of where we are, of how old the universe was before our galaxy existed, of how small our local address is within the structures that contain it, of how much of what exists is forever beyond our reach, accelerating away into a silence that no signal will ever cross. The Milky Way is genuinely small, measured, confirmed, established beyond reasonable dispute by decades of increasingly capable observation, and most recently sharpened by the most powerful space telescope ever built. Our galaxy spans 100,000 light-years. Some single galaxies are 60 times that size. Our local group contains a few dozen galaxies. Some clusters contain thousands. Our supercluster spans 500 million light-years. The observable universe spans 93 billion. At every level of the map, we are a minor entry. But the map is built entirely from information collected by one species on one planet orbiting one star in one of those minor galaxies. The entire history of human astronomy, from Galileo's first telescopic observations through Hubble's deep fields through Webb's infrared portraits of the early universe, represents an extraordinarily brief window of attention directed at a cosmos that has been developing for 13.8 billion years. Webb itself is a product of that attention. A telescope assembled from components made across dozens of countries, launched on a precise trajectory to a gravitationally stable point 1 million miles from Earth. Unfolded in one of the most complex deployment sequences ever attempted, now returning images that no human eye has ever directly seen because they arrive as data translated into light by the instruments we built to receive them. The Milky Way may be small, but it contains something the map has found nowhere else: the capacity to build mirrors and point them at the dark. The capacity to ask what is out there, and to spend decades and billions of dollars and the careers of thousands of scientists finding out. The journey Webb has started is not finished. Every new observation cycle produces findings that revise the picture. The impossible early galaxies will be studied further until the tension between their existence and our models is resolved, or until those models are revised to accommodate them. The Hubble tension will either yield to a systematic error finally identified, or will force a deeper rethinking of our cosmological framework. The dark matter halos around galaxies, including ours, will be mapped in greater detail, and their nature, whatever it turns out to be, will become clearer. The zone of avoidance will become more transparent as infrared surveys improve. The timeline of the early universe will be refined. The atmospheric chemistry of exoplanets will be characterized with growing precision. Every answer Webb provides opens several new questions. That is not a failure of the instrument or of the science. It is the signature of inquiry working at the edge of what is known, the place where every confirmed answer reveals a new horizon, and where the distance between what is understood and what remains unknown is always larger than it was before. We are small. We arrived late. We live in a quiet corner of an unremarkable cluster in a modest supercluster in one filament of a cosmic web too vast to fully comprehend even with the most capable instruments our civilization has yet produced. And we built a telescope to look at all of it. That is not a small thing.